Welcome to this week's video. We will continue our series on soil classification. This week, we will be conducting a hydrometer test in compliance with ASTM D7928-17. In this video, we will highlight the importance of hydrometer testing, conducting a test, and lastly, reviewing and discussing the data established. As you may recall, last week, we conducted a sieve analysis and were able to determine the data on the particle size distribution of a soil sample greater than the number 200 sieve, or 0.075 millimeters in diameter, and we plotted the distribution on a gradation curve. This week, we will determine the particle size distribution of a sample less than the number 200 sieve, as we collected at the end of the previous lab. The primary mechanism of the hydrometer test is particle sedimentation in a solution matrix. To analyze this, Stokes' law from fluid mechanics returns and allows us to determine a particle velocity and eventually the time it takes for the particle to fall out of suspension and settle below. This analysis method works by analyzing the density of the sample solution and recording its change over time. So, the larger, thus heavier particles will fall out of suspension first and result in sedimentation at the bottom. This sedimentation causes the solution density to decrease over time. To capture the time rate change of density, a calibrated hydrometer is used. Due to the various uses of hydrometers, a specific calibration is required. For our lab, we will be using an ASTM 152 H-type hydrometer device, as illustrated. Note the labeled calibration data that has been provided. Here is an example of the completed hydrometer lab test dataset. The only data you're responsible in gathering during the lab period is the data highlighted in the box on the left-hand side of the table as shown. Please note, this data was conducted over a 2-day period and will not be possible for our lab today. Thus, some adjustments to the ASTM standard have been created and will be highlighted throughout the video. With the pre-lab material covered, let's head out to the lab. I'll see you there. Hello, welcome to the lab. If you look around, this is how your area will be set up. On the left, we have our materials to create our soil solution, and on the right, our soil sample and beaker. To create the soil solution, we'll be using a diluted sodium hexaphosphate in the graduated cylinder and blend it with the soil we have collected before. To create your soil solution, mix the soil, chemical mix, and additional water from the squeeze bottle into your beaker, which should result in less than 500 milliliters of an opaque solution as seen. To further the mixing of the solution, a mechanical blender will be used, but first, a couple safety tips. This is the blending head that rotates at a high RPM. Next, your speed level and burst switch on top. To activate the blender, once inserted, the cup will activate this switch on the back, so be careful when starting, just like this. Now that the process is covered, let's do it. Take your less than 500 milliliters of soil solution and slowly add all the material into the blending cup. You may use some additional water from the squeeze bottle to rinse the beaker to remove all material. Your goal should be roughly 500 milliliters of solution inside the blender cup. Now that we have our complete solution in the blender cup, carefully attach the cup to the blender and mix for roughly 1 minute. Now that our soil milkshake is done blending, carefully remove from the blender. making sure to capture any losses. And note the minimum surface foaming. Just look at the difference from before. Our next step will be to fill the hydrometer 1000 milliliter beaker. Note the 1000 milliliter mark etched into the glass. To do this, we will be using additional water mixed with our soil slurry mix. Start by emptying out the contents of the mixing cup into the hydrometer beaker. Notice, we still have soil material in the cup, so again, use the squeeze bottle to remove remaining deposits into the hydrometer beaker. Next, use your beaker to get as close to the 1000 milliliter mark as possible. Then, finish off with the squeeze bottle, ensuring all particles are below the 1000 milliliter line. With our beaker filled, we need to ensure all water and particles are mixed thoroughly. So, apply a moistened cap onto the beaker and rotate about itself every second for about 1 minute to ensure proper mixing has occurred. With our solution finally mixed to the 1000 milliliter mark, carefully remove the cap and ensure there are no minimum losses. After 2 minutes, take your first hydrometer reading. To do so, place the hydrometer at roughly the buoyancy point and let rest for a few seconds. Then record the time elapsed in minutes and the hydrometer reading. Once the hydrometer has stopped bobbing and is still in the solution, remove the device. Do so by lifting upwards gently with minimal drippage, and then dunk into an additional beaker filled with water. And finally, spin to remove any remaining soil particles. Note, keep the hydrometer in the water-filled beaker in between each recording. Next, add your thermometer to the beaker. Let sit till it equalizes, record the value, then remove and rinse as well. After recording the 2-minute reading, also record the 5, 15, 30, and 45-minute mark. After all your iterations have been completed, an area cleaned according to the TA or instructor, you are done for the lab for the week. With the physical lab component complete, let's move on to the data analytics through an Excel sample, and then highlight a few discussion questions to complete the video for the week. Going back to the example highlighted earlier in the video, this should be the data collected during the lab up to the 60-minute mark. As seen below, several coefficients and factors are pulled from various tables to conclude our calculations. Note, this example goes up to the 60-minute and beyond mark, and due to time constraints, we will record up to the 45-minute mark instead. The first factor to be looked up is the correction factor C. This is pulled from the temperature correction factor table based off the water temperature reading found at the lab. The corrected hydrometer reading R is the H plus C factor combined. The effective depth L is pulled from the hydrometer reading versus length table in centimeters. The next value to be looked up is the K factor. This is pulled from the temperature versus specific gravity table, which we are assuming is to be 2.70 for this experiment sample. Next, to calculate the diameter of particle D in suspension in millimeters is to compute K times the square root of L over T, all in the given units found earlier. The final calculated data point is the percent passing, which is the R, times A factor from the specific gravity versus A table, divided by the M coefficient, which is the weight of the hydrometer test, over the percent passing the number 10 sieve times 100, which in our case was 64.4. With percent passing calculated, you should be able to complete the final soil gradation curve by combining the new data with last week's sieve analysis gradation data. Here is an example of a completed final gradation curve after conducting a sieve and hydrometer test. Notice how data from the sieve and then the hydrometer were combined to form a single gradation curve. As you can see, this sample has a significant portion of fines collected in the pan from the sieve analysis, resulting in a lower M value, thus a significant percent passing with the various iterations of the hydrometer test. For our lab, we have a more sandy soil, so we won't have such high values as found in your data. The last segment of this week's video is the discussion questions. Please answer the following 3 questions in your discussion section of the lab report thoroughly. Thanks. I'll see you next week for our continuation of soil classification series. Goodbye for now.